constructing shared worlds. So yeah, thanks for being here, Toby, and look forward to it.
Cool, thanks. Okay. Thanks, everybody. So I'm wearing this sweatshirt which says Ubuntu on it. And this isn't just like a computer operating system, it's also like a concept in philosophy. And one of the things that's kind of curious to me about so far this today in this workshop is that we've been talking about categories, but actually we talk about consciousness, we talk about like different agents, but you know, the kind of fundamental bit of category theory is the Uneda level, and it says the way to understand things is by how they're all connected, and that's also what this Ubuntu philosophy means. It says, like, the way to understand my being is through understanding how I am with everybody else. And so, kind of, it's almost as mysterious, more like my experience of the world inside my head, and I imagine, like, so do all of you. Obviously, I don't know that, but I imagine you do. And yet, you know, those worlds kind of might be different and people can disagree, but at the same time people can agree lots of the time, and they seem to experience the same kinds of things, and maybe that's because there's a world out there, or maybe it's not. As far as I'm aware, all I have is like my sensations, and somehow like we agree about what those are. Oh, I should measure how long I've taken. And so, this is kind of like very preliminary work. I've kind of didn't take as much time thinking about it as I might like to have done. I kind of started mentioning it to like Clere Smithe over there. But this is kind of like a proposal for like some of the things that I've been thinking about along these lines. Because it's striking to me that often when we think about agents, we just think about like a single agent, and that's kind of like not very much in the spirit of like this kind of categorical language. And so in the beginning, I'm going to talk a little bit like Sean was doing about perception and the proximate inference in a kind of explicitly kind of like categorical cybernetic language. Because there's a lot of work being done in that world that's kind of quite nicely related to questions about like the structure of agency. But it seems somehow to me that that's not quite like enough. Like approximate inference isn't enough to give you what we call active inference. Like also we act out in the world, whereas the sort of perceptual model just tells you like how to predict the stuff you're going to perceive. So there's kind of like a bit more here, and the bit more is that like I predict like what I'm perceiving, but I also maybe do some prediction which leads to actions, and then those actions go out into the world and like affect the rest of you guys. And that's where I'm going to talk a bit about like polynomials, kind of in the sense of high school algebra, but also a little bit more like categorified. I'm sure lots of you where I've like work in applied category theory at the moment, basically like largely due to David Spivak about polynomials. And the thing is, these polynomials, they're not like the key part of the story. Like I'm basically saying you have some like language of interaction, or some like algebra of interaction, but for me it's going to be polynomials. And then I have this concept which is like cheeky polynomials, like called daisugi, and I'll show you a picture of that. Some of you may know what that is, at least in the world. It's just some concept I've made up in maths. And then I'm going to use that to talk a little bit about like how maybe we come to like share this world in a kind of active inference way. Okay. Oh yeah, some of my slides for some reason have a lot of blank space in them. I don't know what it is. Okay, so maybe your Bob didn't stand over here. So perception. The idea is like what Sean was saying earlier, that we have like in our brain some belief about like how the world generates like the sense data that we get. That's this thing that is called a generative model. It's a kind of like structural thing. It's like our belief about how the world is set up, like its causal structure, along with some belief about what the current causes, like of our current sense data are, and those things that I think we might call perceptions. And I'm going to be very agnostic about like the relationship of these perceptions to like qualia or whatever. Sean indicated that there are people who make connections between this kind of free energetic language and consciousness, but I'm not going to talk much about that today. We can talk about that later. But sort of mathematically, this thing, as Sean was saying, is formalized as something like this stochastic channel or conditional probability distribution, which says, okay, given some like belief about causes in X, like so what stuff is out there, I can make a prediction, probability, or I obtain a probability distribution about Y, which is like something like the sense data that I'm expecting to receive. And this like thing that I'm calling a perception is really just a state of this X, or a distribution over X, a distribution over what those causes like might be. And then the idea is, and I think it's, it's just a hypothesis, but there's lots of nice evidence to suggest that this is a good idea, is that the brain updates this pi distribution over time using Bayesian inversion or approximate Bayesian inversion to maintain a sort of veridical belief about what's actually out there, according to its generative model. And I emphasize this according to, because it's just a subjective thing. It's like a model you've got in your brain. It's not necessarily true about how the world is, but evolution might have selected you to have a true model or an approximately true model, but it's still just a subjective thing. Okay, and I'm going to say a little bit about approximate inversion from a sort of categorical language, in a categorical language, because it ties into this kind of categorical cybernetic stuff I mentioned at the beginning. But basically, as I mentioned, we've got this predictive thing, which is this channel, and it kind of goes in a sort of forwards direction out from me towards the world. And then this update thing, it takes in a probability distribution here, which is my prior belief, my belief about what the causes actually are, and it gives me a way of inverting, so observing data in Y, my sensory data, and obtaining a new belief, which is the belief about what's actually happening right now. And so this pair of C and C prime is the thing I call a Bayesian lens, and they compose in a particular way. In particular, the two forwards predictive channels just compose these stochastic channels in the way that Sean wrote on his slide. That is, you put one after another and you sort of marginalize out the middle variable. And the backwards maps, they sort of do the same thing in the backwards way, but in order to kind of figure out what the intermediate belief is about the intermediate level of causality. Say if you're looking at a big screen like this, you might have a prediction about what's in this patch and a prediction about what's in the whole image, and you need to produce an updated belief about this when I change slide, and then you could use that to produce an updated belief about the whole image, and that inverse process sort of goes in the opposite direction. So we have to do some funky thing here, which is called the lens rule, and I don't really have time to explain because it's not really the subject of this talk. But the point is that there is this nice compositional structure, and in particular, Bayesian inversions compose according to this structure. So if you want to invert what's known in the active inference literature as a hierarchical model, you just need to invert the two parts and then compose them in this way, according to this rule. And that gives you the inversion of the whole thing. And so that's what results in in the sort of dynamics of predicted coding, you kind of get local dynamical systems that allow you to do this. And that's a kind of functorial assignment of dynamics to these channels. So that has this nice sort of locality property. And it means you can draw pictures. Of course we love pictures, and so we can draw the sort of thing that points towards the world as going like this, from left to right, and this is my belief about what's actually going on. And then if something happens out in the world, and I can sort of go back and I obtain a new belief. And that's nice. This is a kind of nice compositional picture thing. But this sort of points not from often when we think about processes in process theory of categories, we think of the morphisms of representing changes in the world. And so you take one step, and I take another step, and that's what each of these boxes does. But the thing is, these aren't changes in the world. These are just ways to zoom into the world. And so you're really pointing kind of into the world here, as I say, not sort of through the world. And when you come to think about how systems in the world sort of couple together, they kind of are like these little cells or boxes, and they kind of swim around and they sort of plug into one another and they sort of talk to each other, and then they can recouple. And this is a kind of slightly different story of composition, and I'm going to draw a picture in a moment which kind of puts this on top of this. Just as an interesting aside, both of these kinds of composition follow this kind of lens rule that I mentioned, but they're kind of different kinds of lenses. It doesn't really matter what the data of this composition is right now. We can talk about it in a minute. I don't want to take up all the time on the sort of technical details. Okay. Yes. So, as I mentioned, we're sort of tempted to do something like this, which is very informal. We take this diagram, which I drew sort of from left to right, with a state on the side that gets updated, and sort of put them in on top of the boxes, and then somehow we couple the boxes together, and we need to couple these diagrams together, and it's not totally clear how we do that. There is a kind of story emerging about how this thing kind of works, but it doesn't really tell you, at least, how to relate these two states up here, for instance. So for instance, we might want to say, okay, well, when we come together, we might like form part of an organization with a particular aim, like in a company. And so we work together towards a common goal. Or like I started with at the beginning, we might want to say, okay, well, we all have some shared belief about the world that allows us to communicate. And so just putting these things in boxes and saying, okay, well, we've got states doesn't really tell us about like how those two things are compatible in any way. So that's this problem here of like, as I mentioned at the beginning, of like subjectivity of these models is like, okay, well, there's just one model per system. And you know that we often focus on just like individual systems to the detriment of like how we're sort of all coupled together as a whole like society. I don't really think that we really have much of a world without this notion of society. And then there's a kind of other problem which I should have probably put second, which is the problem of action. Like this thing can act, this thing like makes a prediction maybe about like how it affects the world, and so does this one, and that actually results in the world changing in some way. But like it's not quite clear like how we might do that. And so effectively what we want to do is somehow like figure out the linguistic tools, as it were, or the grammar of the sort of coupling of these two kind of mathematical languages. Which is, you know, this is like a proposal for that kind of thing. As I say, I'm using this language of polynomial, I'll be using this language of polynomial functors, but we don't have to choose that language. It's just a particularly nice choice of sort of language of interaction. Okay, so this box here is a thing that we might know from elsewhere as a wiring diagram. I labeled the inner boxes as P and Q, and these are going to be objects in this category. Effectively, they'll be polynomial functors, which is something I'll explain in a moment. And I suspect David Spivak will explain this in more detail tomorrow afternoon when he gives his talk. So I'm going to rush, but hopefully it'll make some sense as time goes on. But in particular, this wiring diagram is a morphism in this category of polynomials, because really the morphisms tell you how these objects wire together. I mean, that's, as I said before, like what these monoidal categories do. And so here we can sort of put this key box next to this key box in this world, and then somehow wire them up to produce this R box. So they kind of come together to form a joint sort of composite system. This is this kind of morphism. It's also known as a dependent lens. And if you want a sort of formal sense of what this category is, we can think of this as a category of co-products of co-representable co-presheaves, or as lenses in this like self-indexing index category. It's like a codomain vibration, but where you sort of take the opposite of each fiber. And because I want to use this language a bit in what comes, I'm going to tell you a bit about how we can sort of unpack these P's and Q's and things. And so you can write, okay, so like if you have a category C, it's if you have an object B, the co-representable on this thing is this functor C to say set that gives you the Hom set. And we could call this like Y to the B just for like the concision. And so this gives you like a formal notation for these like polynomials. So you choose like an indexing set, which I call for technical reasons P of 1, and following David Spivak's notation, and you sort of take their sum. And that says, okay, well, for each position or each configuration in this set, I think of this set as like representing all the possible like shapes or like, you know, configurations that a system might have. For each possible configuration, we have like this thing, this other set here, which is I think of as like the types of like sense data that it might receive, that the system might receive in that configuration. So, for instance, when I've got my eyes open, I can receive different or more data than I can receive when I close my eyes. And so that means that like the way we interact with the world can sort of depend on what we're doing. And in particular, when we're interacting, we can sort of couple together in a way that affects each other's like shape effectively. And a morphism of polynomials is something that says, okay, well, how do I relate the configurations of P to the configurations of Q? This is a function. And then it's got this little backwards thing. Again, as I mentioned, it's a kind of lens. And the backwards thing says, okay, given like the sense data of Q that Q should expect in the position given to it by this morphism from the configuration of P to Q, how do I like sort of effectively map back to the sort of sense data that P should expect? Effectively what this means is like, given some input to this R box, how do I obtain inputs to the P and Q boxes inside? Like, so we think of this as like, as I mentioned, it was like zooming into the world, like looking down at how the world is from like sort of a bird's eye view. And of course it's a monoidal category, and it's in particular a monoidal closed category, and this means that you can put two systems together. And not only can you put two systems together, but you can also think about how how the systems are wired together, so internally to this category poly. So this polynomial of like QR says it sort of encapsulates all the ways that Q might be configured to like wired up to R. And so we can use this, I'll use this in a minute to talk about the systems that sort of predict how they are arranged in their universe in some sense. Okay, so that's a very, very brief introduction to this category poly. And so so I mentioned that this sort of approximate inference thing, it just does perception, but in particular these kind of like, the kind of total spaces of these polynomials have this particular type in some sense. Okay, I forgot to mention that we can represent polynomials as this kind of like bundle thing here. And we can sort of aggregate all of the sort of sense data into like this one object. And then this would be a lens or a predictive system which says, given some belief about where the system is in the world or in its like, world model, it says, okay, well I make a prediction not only about my sense data, but also about like the configuration that I would be in to experience that sense data. And I just also want to point out that this subsumes the kind of thing that people often do in the active inference literature, where they write, okay, well, given some like latent belief, I make a prediction about like my actions and my sense data, because this is effectively the sum of A and A times S. So it's S times the sort of positions or configurations of the actions. And so we think of configurations as like actions. When I change my configuration, it's like taking action in the world. This is like the same kind of notion as you get in the active inference literature as Markov blanket, except it's a bit more general. As I indicated, it allows you to talk about systems where they can sort of change their shape or they can perceive differently depending on what they're doing. And obviously where I'm going with this is that we can use this language of polynomials to talk about how these things can couple together. But in order to do that, we have to answer these three questions. The first one is like, what is this X? Like I said, it was like the latent space or the space of beliefs that the system has about its world, and that's not really like very informative. What on earth does that mean? And like, how actually do we do this wiring if I've got some like P thing and I've got some Q thing in the world and they kind of couple up? Like, as I mentioned before, like what does that actually mean for their models? And can we write down a model for the composite system? Under what circumstances are we licensed to do that? And then the third question is like, okay, so suppose we do have a situation like that with a P system and a Q system in a world that's sort of wired together, and like they're maybe part of a company. Like, how does the company actually act in the world? Or how does the organism actually act in the world when it's made up of cells that are all acting together? Like, how do you get a coherent action out of a group? Okay, so the basic idea is to say that this X thing, as I sort of indicated a moment ago, represents a model of the agent's world. This could be like physically and parametrically. So I come from this like, I'm trying to understand, say, this like world of the free energy principle, which generally speaking is supposed to like apply to all kinds of adaptive systems. And it's supposed to say, in some sense, you can understand them all as doing some kind of approximate Bayesian inference. And so it spans from brains to like cells, and it's quite sort of congruent with ideas that say all things have a kind of notion of like kind of being or like conscious being or adaptive being, even if it's trivial. And so a good example for like this kind of world model might be like cells in a sort of warm bath or like maybe near an ocean vent. They can move around in this world, but they also move around in like their sort of configuration space, so that's like their temperature. And so maybe if they go too close to the vent, then they die because it gets too hot. If they move too far away, then it's like, they don't have enough nutrients, so they can't survive as well there. And so there's a kind of like dependence on where they are in this space as to like what kinds of possibilities are open to them. And so the system then like is supposed to, according to this like this kind of story, choose its actions in order to make its beliefs come true. And this is what Sean was saying earlier about predictive processing. You like have this belief about how the world is, and then you make it come true by taking action. And the way you do that is by assuming that you will make it come true. And you sort of deduce on that basis like what actions you need to take in order to for that thing. It's kind of self-fulfilling. But a lot of this kind of cybernetic stuff has this sort of tautological flavor. But nonetheless, this story still leaves this kind of problem of solitude. And so like, how should we relate this P to X, and how should we like couple these things together? And the idea I've had, I don't know if it's a useful idea, but you know, it seems to go somewhere, and as I say, this is just work in progress. But it's to say, okay, well actually maybe this whole polynomial should have some dependence on this X as well, in the sense, as I indicated with the cells in this kind of heat bar, that their sort of possible configurations might depend on where they are in the world. And that's just, you know, another morphism, another, say, function that just projects the configurations down onto this, like, configuration space. So that means acknowledging that this P may also depend on X. And so what we do is we say this world model has to be like a, what we could call like a stochastic section of X. That means like I make a prediction, given, I have a belief about where I am, and I make a prediction about, you know, where I think I'm, you know, what I think I'm going to experience, what I'm going to be doing. But that prediction should maintain my belief about where I am. And that's a kind of trivial thing to say, but it's important for making the kind of mathematics work. Okay, but before, I didn't make any condition on the polynomials like this. This is just some other thing that I've done just now, and so that kind of, does that ruin the structure that I started with? The answer is luckily no, and that's what this like concept of, yeah, that's what this concept of daisugi is. And in like, as far as I'm aware, in Japan there are these things called daisugi, which is a kind of method of coppicing trees. And like the idea is that somehow you cut the tree to make logs that are nice and easy to harvest, without like killing the tree. And then, you know, in Europe there are other versions of coppicing which are not as nice as this, but this is a particularly beautiful way because you get like trees on top of trees. And the reason I named the thing I'm going to introduce in a moment, daisugi, is that you can think of polynomials as like trees because of the way they compose. Like their possibilities sort of branch into the future, and as you compose them, they sort of branch out. And these things are kind of like bundles of these trees, in the sense, in the sort of spatial sense. So like bundle upon it, like Shiki polynomial, it's a daisugi. Okay, so the key point is that this category of polynomials can be instantiated in any locally Cartesian closed category. That's a category that every slice is Cartesian closed. In particular, like that's a kind of detail. It's not super important because actually you can sort of do this with less structure. It's just an easy thing for me to say just now. So in particular, if the category that we're interested in, as I indicated, we might want them to be like have objects which are some kind of spaces. So if they have this kind of spatial structure, if it's like a topos of spaces, then we can instantiate poly in each of its slices, and that gives you, I mean, if you just do it, you just get this triangle, and because this morphism has to be equal to this composite, then that gives you this this thing I drew just here. So the objects of this are really the things that I wanted, and effectively this category of Shiki polynomials of daisugi has all the, you know, has the structure of poly that we wanted, say this tensoring and this internal harmony, it's all very nice. And as I mentioned, this bundle at the bottom represents like which configurations are available to the system across the space there. So as I said, like the cells in the heat bath, like there might be some place where there's no configuration available to them. So that just means like this, like P to the 1 just goes to the empty set, say, in that place. Okay, yeah, and then the section of this daisugi just tells you how sense data depend not only now on the configurations adopted by the system, but also on like the location of the system in its configuration space. Okay, not much time, but I want to say briefly some technical stuff, which is that this defines a stack. Some of you may know what a sheaf is. This is like a categorified sheaf. In particular, it's like a sheaf where the hom sets are sheaves to, so we can, as I say, restrict to like our attention to some part of the state space and say, okay, well, if I restrict to like this part over here and this part over here and they overlap, then they sort of agree on the overlap in the middle. And this is also true of the morphisms, which tell you how the sort of parts bind together. And that's what kind of makes the stack. And so we can sort of zoom in on how they fit together. And the sort of the thing that, the main reason that I'm motivated to think about this structure is that we can then use sheaf theory, in particular like cohomology, to measure like when the systems actually disagree about their world models. And so to say, okay, well actually, what are like how do we like overcome disagreements? How do we actually obtain this like shared world? It's because like it's through this process of say minimizing instruction, and in like the literature on like applied sheaf theory and applied topology, there are people who use this kind of to talk about how we might build like sensor systems which like form a sort of coherent view of the world, or how in social networks people might like come to have opinions that are not too divergent from one another. And yeah, I don't want to get too much ahead of myself, but the point, how much time do I have? 0. Well, okay, the next thing is just that this assignment of sections to these daisugi also defines a sheaf. We can then use this internal HOM to like model how systems around the system of interest behaves in the world. We can then do this for multiple systems in the same world. They all have like their own model of how the system is going to behave. And assuming that the agents all agree about what the world is, that is, we've got like a sheaf and not just a pre-sheaf, like we can sort of talk about like how this sort of joint system might behave. We can sort of talk about what their joint model is. But really, the kind of more interesting bit of the story is like about like when there are actually disagreements and like what we can do about that. And that's the bit I don't know much about yet. And luckily, I ran out of time, so I don't have to pretend I do. Thanks.
We have time for questions.
Oh, well, I thought I ran out.
That was excluding questions.
Oh, yeah. Okay.
Would you like to do another slide?
That's okay.
If you want to do today, then.
No, that's fine. Yeah, okay, sure.
Yeah.
Just one slide. So the point I was trying to make here is that earlier I said that the system is trying to predict like what's happening on its boundaries. It seems to me that a kind of more interesting thing that an adaptive system is doing is really predicting like how the world is configured, and then how that configuration produces its sensor data. And that's effectively say predicting like the content of this internal HOM thing, which is like the way that the world is organized, so how P is related to the rest, which is this like HOM, the rest of the world, to its boundary, and its boundary of the universe might just be trivial, but it could be like a corporation. And then once you've got this whole collection of things defines like another stack object, and we can sort of ask like, okay, well, given a collection of these things that are all predicting how each other's predicting, like what's going on there. That's enough.
Thanks again. Questions, 3 minutes. Yeah, where's the question? Any question? That's good. Yeah. There's one. Go ahead.
So there was a part where you were talking about how you can use this to kind of find out when there are disagreements, right?
Yeah.
That's especially interesting to me, and I was just curious. Are you familiar with like in the philosophical literature and sometimes in other literatures, there's this idea of like common ground. In linguistics, some people have talked about how like when common grounds are not in sync, that means there's like a miscommunication happening, and how that might fit into sort of this structure that you've built, right? Like it's really interesting.
Yeah, that's obviously what I'm trying to get towards. I haven't got there yet, but I needed to set up this structure in order to like. So yeah, the thing I wanted to say at the beginning that I didn't say, which is that this is like a workshop about categories as applied to a bit of science, and I wanted to say a bit about why I like this kind of language. And it's, for me, not only is it because it's about like relation and interaction, it's also because I find that using this language forces me, I think this is probably true about using mathematical language generally, but because categories are all associated with types, and you have to like put a type on everything you say, it's a kind of discipline, and it forces, at least I find, forces me to think clearly about the things that I'm trying to say. And so I find that if I can't say something in this language, it means I don't really understand it. And so my motivation for setting up this stuff was to be able to say things that I found to be sensible about the kinds of things that you would just indicate.
Yeah, there's another question. Yes, yeah.
Yeah, Toby, fascinating, thank you. That's really, really entertaining and educational. I've not come across this. I have a question. You put a big emphasis on the use of language.
Yeah.
And I think you've put some effort into the way that you communicate this. And so my question is very specific to your intention about multi-agent worlds. Are you saying that there are many agents and many worlds, or many agents and one world, and that distinction you said about the subjective model, is that the open question? I'm not sure, because I've noticed you're really focused on being careful with language.
Yeah, so I am inclined to say, though obviously it's not a fact or anything I can prove, that I would associate a world to each agent and say that the degree to which they share a world is somehow like equivalent to the degree to which they can communicate in a sensible way. And that's kind of, to me, like something that you see in like, you know, socio-political situations at the moment, that you get people in these, you know, bubbles and they find it hard to talk to each other. That's somehow like they don't share a common language. And that's, you know, it's a kind of impossible, it's like a sort of topological failure somehow. You can't like talk, it's a paradox. Maybe not quite as extreme as that, but like, to come to common ground is to say to sort of erase those boundaries. And that's one of the things that, you know, humans are good at, in principle, and like, it's interesting that, you know, say, connectionist systems are kind of good at, but we don't really have nice mathematics for yet. It always strikes me that, well, it always seems to me to be the case that if one marker of success of this applied categorical machinery would be that people use it informally, and that they don't have to just like prove every morphism exists, because actually they might just have like empirical data to substantiate their claim. And so I'd be happy to see this kind of stuff be used in a kind of informal way. It's kind of interesting that applied category theory comes out of mathematical computer science, but people really want things to be very tightly proved. But actually, the world isn't often so precise as that. And so, yeah, I think, you know, there are lots of
The reason I ask, sorry, maybe we can chat later on.
Yeah,
The reason I ask is that there's this book that's causing a bit of consternation. It's those boys from Chevron, I forget the name now, that they've just been associated with David and Brenda.
Yeah.
And there's this book that they've just published. I think it's a load of crap. I hope it's not. But it's exactly this point, which is that, you know, we can use these category theory constructions in order to make sense of this, I'm going to say multi-agent world. And it really, they never go to the extent you did. I wish they'd have been here today. Anyway, that's why I'm asking.
I am aware of the book, though I'm not aware of the constellation.
You're not missing anything.
I guess I was aware of the book existing. I thought, okay, it's good that such a book may exist, but I haven't read it, and
Yeah, anyway,
I'm curious about. I mean, I don't follow.
Let's go. I'm sorry, we're successfully went over time.